Hello. Hello. Hello.
ഹലോ.
ഹലോ. ഹരി കേൾക്കാനുണ്ടോ?
കേൾക്കാം.
ഓക്കെ. എന്നാ പിന്നെ സ്ലൈഡ് ജസ്റ്റ് ഒന്ന് ഷെയർ ചെയ്ത് നോക്കിക്കോളൂ.
ഇതൊന്ന് ഷെയർ ചെയ്ത് നോക്കാം. ഹോസ്റ്റ് ഡിസേബിൾഡ് പാർട്ടിസിപ്പന്റ് സ്ക്രീൻ ഷെയറിംഗ്. എനിക്കൊന്ന് പെർമിഷൻ തരണം എന്നാണ്.
യെസ് അത് ഞാൻ നോക്കുകയാണ് എവിടെയാണെന്ന്. ഞാൻ ആദ്യമായിട്ടാണ് ഈ മീറ്റിംഗ് ഹോസ്റ്റ് ചെയ്യുന്നത്. അപ്പൊ ഞാൻ ജസ്റ്റ് മേക്ക് ഹോസ്റ്റ് എന്ന് പറഞ്ഞ ഒരു ഓപ്ഷൻ ഉണ്ട്. പക്ഷെ അത് ചെയ്താൽ അപ്പോൾ എല്ലാ കൺട്രോൾസും ഹരിയിലേക്ക് പോകുന്നത് തോന്നുന്നു. കോ ഹോസ്റ്റ് ആക്കാനുള്ള ഓപ്ഷൻ ഉണ്ടോ നോക്കട്ടെ.
കോ ഹോസ്റ്റ് ഓപ്ഷൻ ഉണ്ടല്ലോ.
ഓക്കെ.
ഹോസ്റ്റ് ആയിട്ട് ആഡ് ചെയ്യോ? അതിന്റെ ആവശ്യമില്ല എന്നുണ്ടല്ലോ. സൂം അങ്ങനെ അധികം ഉപയോഗിക്കാത്ത കാരണം.
ഞാനും സൂം അങ്ങനെ ഉപയോഗിച്ചിട്ടില്ല. അല്ല, ഇതില് അലോ ഓൾ പാർട്ടിസിപ്പൻസ് ടു ഷെയർ സ്ക്രീൻ ഉണ്ട്. പക്ഷെ അതാണെങ്കിൽ പിന്നെ ആർക്ക് വേണമെങ്കിലും സ്ക്രീൻ ഷെയർ ചെയ്യാം. പക്ഷെ ഓക്കെ, തൽക്കാലത്തേക്ക് ഞാൻ ആ ഓപ്ഷൻ എനേബിൾ ചെയ്തിട്ടുണ്ട്. ഷെയർ സ്ക്രീൻ എനേബിൾ ചെയ്തിട്ടുണ്ട്. ജസ്റ്റ് ഇനി ചെയ്യാൻ പറ്റുമോ നോക്കിക്കോളൂ.
ഓക്കെ. കാണുന്നുണ്ടോ?
കാണുന്നുണ്ട്. ഫുൾ സ്ക്രീൻ ആക്കി നോക്കിക്കോളൂ.
ഫുൾ സ്ക്രീൻ. ഓക്കെ. കാണുന്നില്ലേ ഫുൾ സ്ക്രീൻ?
ഫുൾ സ്ക്രീൻ കാണുന്നുണ്ട്. ഓക്കെ, ആനിമേഷൻസ് ഒക്കെ വരുന്നുണ്ട്. പിക്ചേഴ്സ് കാണുന്നുണ്ട്. എന്തെങ്കിലും എഴുതാൻ എന്തെങ്കിലും ഉണ്ടോ? എവിടെയെങ്കിലും എന്തെങ്കിലും
എഴുതാൻ? ഇല്ല, എഴുതാനൊന്നുമില്ല.
സ്ലൈഡ്സ് തന്നെയല്ലേ? ഓക്കെ.
സ്ലൈഡ്സ് തന്നെയാണ്. മാത്തമാറ്റിക്കൽ അങ്ങനെയുള്ള സ്ലൈഡ് ഉണ്ടാക്കിയിട്ടില്ല.
ഇത് നല്ല കാര്യം. PhD കാര്യം പറയുന്നുണ്ടല്ലേ? അത് 9 ഡിസംബർ ആണോ ലാസ്റ്റ് ഡേറ്റ്?
9 ഡിസംബർ. അതെ.
ഓക്കെ ശരി. ഓക്കെ. അപ്പോൾ സാധാരണ ഗതിയിൽ ഒരു 40 to 50 സ്റ്റുഡൻസ് ആണ്, പാർട്ടിസിപ്പൻസ് ആണ് ജനറലി ഉണ്ടാവാറ് ടോക്സിന്.
അധികം MSc സ്റ്റുഡൻസ് ആയിരിക്കും.
അധികം MSc സ്റ്റുഡൻസ് ആണെന്ന് തോന്നുന്നു. അത് അറ്റ്ലീസ്റ്റ് കുറച്ച് പേരെ നമുക്കറിയാലോ. അതായത് നമ്മുടെ അപ്പോൾ ഈ ഗ്രൂപ്പിന്റെ ഒപ്പം പ്രൊജക്ട് ചെയ്യുന്ന അങ്ങനത്തെ കുറച്ച് സ്റ്റുഡൻസ് ഉണ്ട്. അപ്പൊ അങ്ങനെ കുറെ MSc സ്റ്റുഡൻസ് കാണാറുണ്ട്. പിന്നെ ബാക്കി അറിയില്ല. പക്ഷെ കൂടുതൽ BSc MSc ആണെന്ന് തോന്നുന്നു. ചിലപ്പോൾ ചില പ്രൊഫസേഴ്സും ജോയിൻ ചെയ്യാറുണ്ട്. ഇപ്പൊ MG യൂണിവേഴ്സിറ്റിനൊക്കെ ചില പ്രൊഫസേഴ്സ് ഇടയ്ക്ക്
ഓക്കെ
ജോയിൻ
ഓക്കെ.
ചെയ്യാറുണ്ട്. അപ്പൊ അവരുണ്ടാവും. പിന്നെ ഈ KTP ഗ്രൂപ്പിലുള്ള കുറച്ച് ആൾക്കാർ ജോയിൻ ചെയ്യാറുണ്ട്. സാധാരണ ഇത് കണ്ടക്ട് ചെയ്യാൻ ഒരു IACS കൾട്ടിവേഷനിലുള്ള ഒരു പോസ്റ്റ് ഡോക്ക് ആണ് സാധാരണ കണ്ടക്ട് ചെയ്യാറ്.
ഓക്കെ
ഇന്ന് പുള്ളിക്ക് കുറച്ച് തിരക്കായത് കാരണം അപ്പൊ ഇന്ന് എന്നോട് ചെയ്യാൻ പറഞ്ഞിട്ടുണ്ട്.
ഓക്കെ ഓക്കെ ഓക്കെ.
ഹരി മുമ്പ് ഇങ്ങനെ ഓൺലൈൻ ടോക്ക് കൊടുത്തിട്ടുണ്ടോ?
പക്ഷെ മുമ്പ് ഈ കോൺഫറൻസിന് അങ്ങനെ കൊടുത്തിട്ടേ ഉള്ളൂ.
കൊറോണ സമയത്ത് അല്ലേ? ഇപ്പൊ എല്ലാം
കൊറോണയുടെ
ഓൺലൈൻ
സമയത്ത്.
സമയത്ത്. ഞാനിപ്പോ ഇവിടെ ഗസ്റ്റ് ഹൗസിലാണ്, നോർത്ത് ക്യാമ്പസിലാണ്.
ഓ ശരി.
സോണി ഇവിടെ
എക്സാം ആണോ?
എക്സാം അല്ല. അപ്പോ സോണി ഇവിടെ റോക്ക് ക്ലൈംബിങ്ങിന് പോയിരിക്കുകയാണ്. അതായത് ഇവിടെ സോണിക്ക് റോക്ക് ക്ലൈംബിങ്ങിന് പോകണമെന്ന് ഉണ്ടായിരുന്നു. അപ്പൊ അതിനെപ്പറ്റി അന്വേഷിച്ച് ഇവിടെ ഈ സ്കീ ഡിപ്പാർട്ട്മെന്റിൽ ഒരു ജിനേഷ് മച്ചർ എന്ന് പറഞ്ഞ ഫാക്കൽറ്റി ഉണ്ട്. അപ്പൊ ജിനേഷ് ഇങ്ങനെ പോവാറുണ്ട് എന്നറിഞ്ഞു. അപ്പൊ പുള്ളിയോട് ചോദിച്ചു. അപ്പൊ ജിനേഷും പിന്നെ സിദ്ധാർത്ഥ ശർമ്മ, അപ്പൊ അങ്ങനെ രണ്ട് ഫാക്കൽറ്റീസ് അവരിന്ന് റോക്ക് ക്ലൈംബിങ്ങിന് പോകുന്നുണ്ടായിരുന്നു. അപ്പൊ സോണി അവരുടെ ഒപ്പം പോയിരിക്കുകയാണ്. അപ്പൊ അതിന് രാവിലെ ഇവിടെ അതിവിടെ IIT പുറകിൽ തന്നെ, ഇവിടെ ജസ്റ്റ് ഇവിടുന്ന് ക്ലൈംബ് ചെയ്ത് പോകാനാണ്. അപ്പോ ഞാനിപ്പോ ഒന്നിപ്പോ വെയിറ്റ് ചെയ്യാണ് അവർ തിരിച്ചു വരാനായിട്ട്. ഇപ്പൊ ഗസ്റ്റ് ഹൗസിലാണ് ഇപ്പൊ. ഓക്കെ, ഒരു പാർട്ടിസിപ്പന്റ് ജോയിൻ ചെയ്തിട്ടുണ്ട്. 10:58. ഓക്കെ. അപ്പൊ നമുക്ക് അപ്പൊ ഒരു 11:05 ആവുമ്പോൾ നമുക്ക് തുടങ്ങാം.
ഓക്കെ ഓക്കെ ഓക്കെ.
ഹലോ
ഹലോ.
ഹരി, നമുക്ക് ജസ്റ്റ് സ്റ്റാർട്ട് ചെയ്യാറായി. ആൻവി അവിടെ ഉണ്ടോ? ഫ്രീ ആണോ അപ്പോൾ? ഹലോ. ഓക്കെ, ആൻവി ചിലപ്പോൾ തിരക്കിലായിരിക്കും. ഓക്കെ ഹരി, അപ്പോൾ നമുക്ക് തുടങ്ങാം.
ഓക്കെ.
ഈ മീറ്റിംഗ് റെക്കോർഡ് ചെയ്യപ്പെടുന്നുണ്ട്. ഓക്കെ
ഓക്കെ.
ഓക്കെ, ശരി. അപ്പോൾ ഞാൻ ആദ്യം KTPനെ കുറച്ച് പറഞ്ഞിട്ട് പിന്നെ ഹരിനെ ഇൻട്രൊഡ്യൂസ് ചെയ്യാം. ഹരിയുടെ 2 സ്റ്റുഡൻസ് ജോയിൻ ചെയ്തിട്ടുണ്ടെന്ന് തോന്നുന്നു. അപ്പോൾ ടോക്ക് ഇംഗ്ലീഷ് ഓക്കെ ശരിയാണ്, കുഴപ്പമില്ല. ടോക്ക് ഇംഗ്ലീഷിലായാലും കുഴപ്പമില്ല, ചിലപ്പോൾ സ്റ്റുഡൻസ് മലയാളത്തില് ക്വസ്റ്റ്യൻസ് ചോദിക്കുമായിരിക്കും.
I can mix Malayalam and English.
അപ്പോൾ അങ്ങനെയാലും കുഴപ്പമില്ല, ടോക്ക് ഇംഗ്ലീഷിലായിക്കോട്ടെ, സ്റ്റുഡൻസിന് ജസ്റ്റ് മലയാളത്തിൽ എനിക്ക് ചോദിക്കാം. Okay, so let's get started. So I can see that there are a few students who are not Malayali, so we'll conduct the talk in English, but the students are free to ask questions in Malayalam. അതായത് കേരളത്തിലുള്ള സ്റ്റുഡൻസിന് മലയാളത്തിൽ ക്വസ്റ്റ്യൻസ് ചോദിക്കണമെങ്കിൽ മലയാളത്തിൽ ചോദിക്കാം. ഓക്കെ, അപ്പൊ ആദ്യം KTPനെ കുറിച്ച് ജസ്റ്റ് ഒന്ന് പറയട്ടെ. ഇപ്പൊ KTP എന്ന് വെച്ചാൽ കേരള തിയറിറ്റിക്കൽ ഫിസിക്സ് ഇനീഷ്യേറ്റീവ്. ഇത് കഴിഞ്ഞ 1 കൊല്ലത്തിലേറെയായി നടന്നുകൊണ്ടിരിക്കുന്ന ഒരു ഇനീഷ്യേറ്റീവാണ്. സോ ദിസ് ഇസ് എൻ ഇനീഷ്യേറ്റീവ് ഓഫ് PhD students, postdocs and faculty who are originally from Kerala but now are working in Kerala and in many places outside Kerala. So the main focus of this initiative is to give some research exposure to students in Kerala to mainly theoretical topics. And we intend to do this through 2 main programs. One is like the current lecture. So we are arranging outreach lectures on various research topics by experts in those topics. And we also arrange talks on various skills that are needed for research, like LaTeX and Python. The second program that we have is basically that we arrange research projects for MSc students. So we select students from through a screening process from all over Kerala, and we arrange research projects for them with various members of KTPI. So we have already completed our first batch. The first year batch has just finished, and it was a resounding success. In fact, the very first paper from that batch, it has just gotten published last week, and we do expect that at least a couple more papers will come out from this batch. The second batch has already started their projects and it is ongoing. Okay, so that was about KTPI. Now let me come to the talk today. Okay, let me first introduce myself. So my name is Krishna Mohan. So I'm an assistant professor at IIT Mandi in the School of Physical Sciences. So today, for giving the talk on this interesting topic, we have with us Dr. Hari Verma, who is my colleague in the School of Physical Sciences. He's an associate professor here. So let me introduce Hari Verma by saying a bit about his career. So he did his BSc from Sacred Heart College, Devara, under MG University. And after that, he did his MSc from IIT Madras. He continued in IIT Madras for his PhD. After that, he has been a postdoctoral fellow at Argonne National Laboratory, USA, and at National Taiwan University, Taipei. He joined as an assistant professor at IIT Mandi in 2010. And since 2017, he has been an associate professor at IIT Mandi. His main research interests are electronic structure and dynamics of atomic systems, photoionization dynamics of atoms trapped in Fullerene cage, which is what he's going to discuss today, electron scattering studies of atomic systems, and above threshold ionization studies of atoms under ultra-intense X-ray radiation. Okay, so now without further delay, let us hand over the stage to the speaker. Hari, now you can start your talk.
Okay, so good morning to all of you. So thank you, Krishna Mohan, for the very kind introduction and also briefing about the activities of Kerala Theoretical Physics Initiative. So I'm very happy to know that you people already have a very nice forum and coming up with nice presentations and other works. So it's great pleasure for me to discuss some of the work that we carry out at IIT Mandi. So today I'll be talking on our, based on one of our recent work, which is the intercluster Coulombic decay in endohedral system via plasmonic excitation. So the title looks a bit technical, but we will make all efforts to decode this title. And probably at the end of the talk, you will say that the title looks very non-technical. Okay, so before coming to the work, let me give you a brief introduction about our institute. So as you already know that I am from IIT Mandi. So these are actually different IITs are mapped in this picture here. So I think currently there are 23 IITs. So IIT Mandi is here, almost on the top of India. So if you just keep a reference to IIT Palakkad, so that is here. I hope you can see the cursor. Can you see the
cursor is visible? Yes, the cursor is visible.
Okay. Yeah. So IIT Palakkad is here. So if you travel like almost 3,000 kilometers, you will reach IIT Mandi. So you can also see that IIT Delhi is here. And then IIT Ropar, which is at Chandigarh, that's also here. So normally if you want to travel to IIT Mandi, you come all the way to Chandigarh. And then from Chandigarh, it takes almost 4 hours on road to reach IIT Mandi. So we have a very beautiful campus situated in the Himalayas. So you can see that there are 2 campuses. So which is this one is the South Campus and this is the North Campus. So they are separated by some mountains here. And so in North Campus, mainly all the undergraduate activities like BTech programs, most of the BTech programs happens in this North Campus. And almost most of the research programs and the master's level PG programs, they all happen in the South Campus. So now, actually we have a road that is connecting between these 2 campuses. So these are some beautiful pictures of our campus. So I think this is a close view of the North Campus, and this is a close view of the South Campus here. And you can see that there is a river that is flowing through the campus. And so here you can see a picture with snow. Although we don't get snow every year, but once in a while we get snow. I think this picture might be taken maybe around 2015 or so. Okay. So although we are 3,000 kilometers away from Kerala, so there is a vibrant Malayali group in the campus. So we celebrate all these festivals. So this is a picture taken for Vishu 2022. And this is a picture taken the last Onam 2023. So we have representation from Kerala in student communities, faculty, and also in the staff as well. Okay, so I think many of you are from MSc levels, MSc or BSc levels in Kerala. So let me just introduce you what are the different schools that are available in our school, in our institute. So we don't follow the department system. So we have this, so we call each of this discipline as a school. So we have a school of bioscience, computing, civil, chemical, humanities, management, mechanical, and then mathematical. And then, so we belong to the School of Physical Sciences. So School of Physical Sciences offer different programs. So one is BTech, so this is an undergraduate program. So the selection is mainly through the JEE Advanced. And then we have this MSc Physics. The selection is through JAM. And then we also have IPHD Physics. This is an integrated program for it's integrated program for Master of Science and PhD. So till last year, we used to take our own exam and take students. But from the next admission, we are going through JAM. So if any of you are interested in any of this program, please write the JAM. And then you can apply here through the JAM portal. And then we also have the traditional PhD program. So the admission is mainly through the GATE CSIR and through an interview here. And I think if your institute is within the top 100, I think you can apply directly without GATE and CSIR. So maybe more details. So I think the one PhD application is currently on. So you can go to our website and see the details, the qualification details and all, and the available fields. All the information are available. And please note that the last day is 9th December 2023. So you please share this information with your friends, those who are interested to pursue higher studies in physics. And let us see what are the current research areas in our School of Physical Sciences. So there is atomic and molecular and optical physics. Then we have condensed matter physics. Then we have soft matter physics. We have high energy and cosmology. And in addition to that, we recently started a Center for Quantum Science and Technologies. Probably you might be aware of the recent developments in the field of quantum technologies. So government is putting a lot of initiative to make India as one of the superpower in this field. So with reference to that, we also started one Center for Quantum Science and Technologies. And you can see some of the faculty members. So I think all are not included here. I think this is probably an old photo. So apart from the standard academic program that I mentioned earlier, you can also write to individual faculty members for doing some short-term projects. So whether it is PG or UG, you can always visit our webpage. You find out whether you are interested in any of the work that are carrying out here. Then you can always write to the faculty members. So if it is available, then they will offer some short-term projects. So I strongly encourage to all of you to apply for some of these options. Okay, so my research group, so we are mainly interested in the structure and dynamics of atomic systems. So this work is mainly theoretical and computational in nature. So we particularly explore the photoionization and scattering dynamics of atomic systems. So our current interest mainly focus around the photoionization dynamics of atoms, clusters, and endohedral systems. And then Wigner time delay studies of atomic system. So probably you might have heard about this attosecond physics, which got the Nobel Prize this year. And one of the fascinating application of this attosecond physics is on the photoionization studies. So you might have studied that photoionization is an instantaneous process. So that is just because of the fact that we did not have the technology to resolve such a short time. So currently we have this technology. So that is known as attosecond chronoscopy. So with that, we can see that the photoionization is not an instantaneous process. There is always some delay associated with it. And that delay is of the order of 10 to the power minus 18 seconds. And we call generally that time is the attosecond, 1 attosecond. So 1 attosecond means 10 to the power minus 18 seconds. So there are many contributions. So to the delay, there are many contributions. So till now we work on this Wigner time delay studies. And so, but I'm not getting into the details of this work today. And we also discussed the relativistic correlation and confinement effects on photoionization. And then we also study the scattering dynamics of atomic systems. So you can visit this webpage and see the different activities that is pursued in our research group. Okay. So let me begin. So let us begin this talk. So let me begin with Richard Feynman's famous statement. So once he asked this question, if all scientific knowledge were to be destroyed and only one sentence to be passed to the next generations, what statement would contain the most information in the fewest words. So what he's basically asking is, if some destruction happens to our humanity, so that delete or that destroy all the current technology, but you want to pass some information to the next generation so that they can build or they can rebuild everything from scratch. So what kind of information that you can pass on to the next generation to make this possible? And his answer to this question is that is given here. So that is atomic hypothesis, that is all things are made of atoms. So this is a powerful statement that if you know this, then you can make everything from scratch. So you can actually see the you can just look at the Feynman lectures. I think you probably are aware of his books. I think in his volume 1 itself, he starts with these statements. So the concept of this atomic structure of the material world was the most fertile idea we inherited from antiquity. So atomic physics is at the heart of modern science and technology. So you can see applications of atomic physics in plasma physics, laser physics, meteorology, astrophysics, and atmospheric physics. Then atomic physics plays prominent role in understanding the molecular physics. So that means it plays fundamental role in understanding the chemical reactions and the biological process, medical physics, and it has many other technical applications. And atomic physics played a prominent role in the early development of quantum mechanics. So you might have studied that we started thinking about deviating from the classical mechanics by when we observed some spectra from some atoms, right? So we observed the line spectra, so which could not be explained by using the classical physics. So that is how the development of quantum mechanics happened. And then the atomic physics, many of the atomic physicists played a very leading role in developing the early computer technologies, because at that time, so when computer technologies are developed, so people want to know where they can apply this. So atomic physics was one of the area where they thought that they can apply all these computer technologies for calculation purpose. And atomic physics also play a very significant role in the current quantum technologies. Okay, so I mainly work on the light atom interactions. So I think this simple picture will tell you the details. So you have a target atom, and then which you exposed with light. So light means any electromagnetic wave. And if this electromagnetic wave has sufficient energy, then it can knock out electrons from this system. And these electrons are then, you can collect it in a detector. So this is a simple process of photoionization. And so initially, you might have studied the photoelectric effect. So everything can be explained using this simple looking Einstein equation. So the kinetic energy of the photoelectron. So these electrons are known as the photoelectrons. So the kinetic energy of these electrons is going to be the photon energy minus the ionization threshold. So the energy supplied to remove the electron from the system. And this simple looking equation played a very foundational role in the subsequent development of physics. And so that is why Einstein was awarded Nobel Prize in 1921 for explaining this phenomenon. So these photoelectrons, so they carry a lot of information about the target. So this is an excellent probe for atomic, molecular, and condensed matter systems. And the data is required for many practical applications. Okay, so this is some kind of preview of this work that I'm going to discuss today. So this is a paper which we published this year. So Rashid Shaikh is my student. So he played a leading role in this work. Okay, so what does it deal with? So it actually, so this is kind of a atomic system in the sense. So here I mentioned that, so you have an atomic system. So just take it as kind of some kind of a target. So it can be atom, it can be molecule, or it can be some condensed matter systems. So now my target system is this. So what is the system? So this, you can see that there is a football-like structure here. So that is a fullerene molecule. So this is the molecule. So this is made from the carbon atoms. So the carbon atoms form some structure in the shape of a football. You can think of in that way. So there is a lot of empty space inside. So it is basically a hollow cage. So you can trap atoms, molecules, or you can also put a collection of atoms together, which is known as the clusters. So this is the target system. So you have some cluster, which is made of sodium atoms. So we have 20 sodium atoms in the form of a sodium cluster, which is put inside this fullerene molecule. So fullerene molecule is nothing but the carbon molecule formed by the carbon atoms. So which takes a football-like shape. So this is my target system. And this target system, we expose to an extreme ultraviolet photon. Okay, so this is my atomic system, and this is my light. So this is a light atom interaction I'm talking. So my target system is sodium cluster inside fullerene, which is interacting with an XUV photon. And then you get electrons from this system, so which you can collect it in a detector. And you can see these are, you can view it as something like it, what you see on a detector. So if you just look at these green arrows, so these signals, so you can see some red spots here, red spots here. So these are the signals that is coming from the sodium cluster. And these signals can occur only if this cluster is surrounded by a cage. Right? So you can do the photoionization studies. You can shine light on sodium cluster, but at this energy, so you can look at these energies here. This is the photon energy. So at these energies, you don't get a signal from sodium cluster if it is not confined okay. But if you confine the sodium cluster inside this fullerene molecule, then you get some signals from the sodium cluster. So what enables this is the phenomenon, which is the intercluster Coulombic decay. So this photon, which does some excitations in this fullerene molecule, and that excitation is the plasmonic excitation. And so we will discuss about that in the subsequent slides. And once it interacts with this system, so you have this plasmonic excitation, and once it decays, it transfers some energy to the sodium cluster inside. And because of that, you get electrons from the sodium cluster. So first we have to understand what is this phenomenon. So this is a very recent, recently discovered phenomenon, maybe around 20 years old. So which is known as the intercoulombic decay. So we will first discuss that to understand this paper. Okay, so this is atomic system that I mentioned earlier. So if you make a closer look at this atom, so you can see different energy levels. So for the sake of convenience, we can distinguish various electrons, like we can call the electrons which are loosely bound to the system. So we generally call it as outer valence electrons, and which are more bound to the system, or which are very close to the nucleus. So they are called the inner valence electrons, or the core electrons of the system. So now, if you shine this atom, let's say with light, and if this light has sufficient energy, so it can knock out the electron from this outer shell, right? So once you knock this electron, you are creating a vacancy in the system, and this electron is now come out. So this is the photoelectron. So you have a photon interacting with this atomic system. It is taking away an electron from the system. So you basically get an ion and then an electron, which is known as a photoelectron. Okay. So now consider another case. So where instead of ionizing the outer shell electron, which are the loosely bound, we are ionizing the electron from an inner shell. So that means you have to supply more energy to the system. So this is like a high energetic photon. So once it has a sufficient energy, so then it can knock out this electron and create a inner shell vacancy. But this inner shell vacancy, so this will not be stable, in the sense that if there is a vacancy here, an electron from an outer subshell, so that will come and fill this vacancy. So that means this vacancy, which was originally here, so that decays into this. So you have a vacancy now in the outer subshell. So once this transition occurs, then it shed off some energy. So you will get a photon that will come out from the system. And what will be that energy? So that energy will essentially be the difference between this E3 and E2. So this is a very naturally occurring phenomena. So generally we call it as fluorescence phenomena. So these are the pictures I have taken from the Wikipedia. So these are the fluorescence from, these are some minerals, and these are some fluorescence dress. So you have, so you have an inner shell vacancy that is filled by an outer shell electron. And in this process, some radiation gets emitted. So it essentially means that whenever you have an inner shell ionization, some other process follows up. Whereas in the case of an outer shell ionization, there is nothing much follows up. So it is something like this. So something like, so if you just imagine a classroom. So let's say that if the backbencher, if he leaves the class, it does not make any difference to the instructor in some sense. But if one of the front bencher leaves the system, then immediately there is will be some follow-up will happens, right? Or you can also look at in this way. So like, let's say you are standing in the queue of a movie theater, and you are, so if somebody leaves from the front side of the queue, then all the other people are interested to occupy that space, right? But if somebody from the back, if he leaves, then nobody cares. So whenever you have an inner shell vacancy, so many interesting things will follow up. So earlier I discussed that whenever this happens, whenever this outer shell electron fill this vacancy, so you get photon. But another thing can also possible. So this photon, if this, so the energy that is emitted during this transition process, if it has the sufficient energy, it can knock out another electron from the outer subshell. So instead of radiation, you get electrons. So these electrons are called the Auger electrons. So these are kind of a secondary process. So on the primary process, you have the ionization in the inner shell, and then there is that inner shell vacancy is filled by an outer shell electron, and the energy emitted, that will be transferred to another outer subshell electron, and that will come out from the system. So you have a primary electron. Because of the process that are involved that we discussed now, you also get a secondary electrons. And these electrons are known the name Auger electrons. So this was so this phenomena is known as the Auger decay. So this is the Auger who made pioneering contributions to this field. So now there is a very strong proposal to call this phenomena as Auger-Meitner effect, to give the credit to the Meitner, this lady here. So who actually originally discovered this phenomenon in the context of discussing some nuclear fusion. And but it is Auger who made it very popular. So normally we call it as an Auger process. But this lady is very unfortunate because she even missed the Nobel Prize for her pioneering contribution to the nuclear fusion. So all her collaborators got the award, but she did not get it. So considering many of these aspects, so now there is a renaming proposal that is going on. So normally everywhere. So now this phenomenon is addressed as the Auger-Meitner effect. And this this process happens in a very fast time scale. So this happens in the femtosecond process. Okay, so this is just a summary of what we have discussed so far. So you have an inner shell ionization, and because of this inner shell ionization, so you will have so this electron from an outer subshell, so that fills this inner shell vacancy, and that energy is liberated. So that energy will knock out another electron. And then you get this secondary electron, which is known as the Auger electrons. But this process does not occur in every inner shell ionization. So remember that to make this happen, this energy should be sufficient enough to knock out this electron. If this energy is lower, then you will not see this Auger effect. So we can actually demonstrate this with a simple example. So if you just look at this neon atom here, so its atomic number is 10. So you have 10 electrons in the system, right? So this is the various levels. So you have 1s, 2s, and 2p. So now you are creating an inner shell vacancy. So these are the corresponding energy values here. So you have to supply at least 48.5 electron volt to knock out the electron from the 2s subshell. So you supply that much energy or slightly higher than that so that you can knock out this electron. So that is creating a vacancy. And the electron from this 2p subshell, which is outermost subshell. So one of the electron from the 2p, so that will come and fill this 2s vacancy. So if you just look at the difference between these two levels, so you can see that this is 26.84 electron volt, the difference between these two energy levels. But this energy is not sufficient to knock out one more electron. Why? Because you may think that, okay, it was initially 21.8 and you are getting 26.84. So you should be able to knock out the electron. But this 21.8 electron volt is for the neutral system, neutral neon. So once you are ionizing this system, so then all the levels are getting more bound to the nucleus. So then you can see that this energy will not be sufficient to remove one more electron from the 2p subshell. So you can actually see the energy values in this graph here. Yeah, so these corresponds to the, so these are the ionization threshold for the 2s and 2p. So this is something around 48 here. So you can see the energy values here. And this is for the vacancy, for vacancy creation, you need around 21 electron volt. And this is the delta E. So this is the energy that is getting liberated. So this IP stands for the ionization potential. But once you have the neon once you have the neon plus, then all these levels are getting modified. So then this will be the energy that is required to remove one more electron from the 2p, because now you have a positive charge, and as a result, it gets more bound to the system. So this is around 60 electron volt. So you have earlier seen that the energy that is liberated is about 26 electron volt. So that is not sufficient to knock out one more electron from the 2p subshell. So that essentially means, so if you have this process, so you have a decay, so you have inertial decay, and then photon is emitted, and this photon cannot knock out one more electron from the 2p. So you cannot get this kind of system. So here you can see there are two holes, but you cannot get it because this energy is not sufficient to remove one more electron from the system. So you can see that from here to here, you can never reach this configuration starting from this. So you are actually seeing a red signal, right? So the neon +2 via OJ decay route is closed. You cannot arrive at neon +2 via this OJ decay process. So whenever you see a roadblock, you always look for some deviation, whether you always look whether any deviations available, right? So we can ask this question, can we find a diversion route for a non-radiative transition? It's a non-radiative transition means this OJ transition, because instead of photon, you are getting this electron, right? But in the normal circumstances, you cannot get this you cannot get this electron emission. So no, in all the cases, you always get the radiative decay for a isolated neon atom. So now we are asking this question, can we find a diversion route for a non-radiative transition so that we can get neon 2+. And the answer to this is that, yes, it is possible. And you can get this non-radiative route, or you can get a green signal if you bring another neon atom. So now, as earlier we have single neon atom. So now we are bringing another neon atom. So they are bonded together. So this is an example of a cluster. So cluster is nothing but a aggregate of atoms. It can be 2, it can be more than 2. So here you have 2 neon atoms which are bonded together. And since it is just 2 atoms, we call it as a neon dimer. So as I said, so these are examples of atomic clusters. So these are aggregate of atoms ranging from 2 to few thousands. And the interesting properties of this cluster is that the physical and chemical properties of these systems, they will change with the numbers. So you can, in a way, you can see that you can control the properties of this system by adding more and more electrons. So the single atom may have certain properties, but when you have put one more atom to the system, then it shows a different property. So it means you can actually control the properties of atoms. So these are sometimes called as artificial atoms. And this cluster physics plays a very important role in understanding how collective phenomena occurs. Like so let's say atom has some particular properties. When many atoms combine together to form molecule and then to form a solid, then the solid will have a different properties. So how these properties are emerging from the individual properties of atoms. So these things can be studied by making these atomic clusters. So atomic clusters act as a bridge between the atoms, molecules, and the bulk materials. So let's see what happens when how this non-radiative transition can occur. So this is a neon dimer. So you have, so the two of these neon atoms, so they will have these energy levels. And so they actually make a very weak bond between these two systems. These are examples of van der Waals clusters. So these energy levels of these energy levels are not much affected because of the bonding between these two atoms. So all the energy values that I have discussed, they almost remains the same. So now again, so let us repeat this process. So you have initially you have an ionization from this. It creates a vacancy. And then one of the 2p electron, it gets fill this vacancy. And this photon is emitting. And as I said earlier, this photon cannot remove electron from this neon atom. But it can knock out electron from its neighboring system. Because if you can look at these energy values here, so this is for the neon dimer. So you can see neon subscript 2. So these are the ionization potentials for the neon dimer. So this is the energy required to create this 2s vacancy. And this is the energy required to create the 2p vacancies. And on the bottom panel here, it shows the two-site ionization potential. So two-site means you have two neon atoms. So when you have these two neon atoms, to create one more vacancy in this 2p, that energy required is around this 46 electron volt. So that is lying below this vacancy, this 2s vacancy. So that essentially means that, so this system will decay to, so the ionization happening, let's say this is as a system, a neon. You can just, for the sake of convenience, I just call this as A. So you have an ionization happens in this A, and then this decay happens, and the energy liberated, so that will knock out electron from the B, the neighboring system, the neighboring neon atom. So we say that the system relaxes non-locally. So non-locally means it is not happening in the same system. The effect is happening in the neighboring system. So the system relaxes non-locally by transferring energy to the neighboring atom. So now you can see that there are two neon plus ions that are created. So we don't get neon 2 plus in one site, but we can get neon 2 plus in such a way that we have neon plus in each site. So this phenomenon is known as the interatomic Coulombic decay, because we have two atoms here. So that is why it is called interatomic. And what enables this process, that is basically the Coulombic interaction. So that is why I call it as a Coulombic decay. So this first prediction of this Coulombic decay was done by Sidderbom, and there they did this predicted first on the molecule. It's a hydrogen fluoride molecular dimer. So they predicted this in this molecule. But then subsequently, they also discovered in this neon dimer as well. So it is easy to discuss the atomic dimer instead of a molecular dimer. So that is why I preferred to use the neon dimer to explain this. So interatomic Coulombic decay, you can define it as the way the system relaxes non-locally by transferring energy to the neighboring atom, so that you get two neon plus ions. But then there are many other interesting things can happen, because the same thing can happen in a different way. So this is the direct, so this is what I discussed earlier. So this normally we call it as a direct ICD. And you can also happen in this way. So here what happens is that the ionization is happening in this in this system here, let's say this system A, but this vacancy is filled from the B atom. So in this case, this vacancy is filled by the A atom, but here the vacancy is filled by the B atom, and then the energy liberated is used to ionize the outer subshell of the A atom itself. So again, so if you look at these two processes, you will have the same final state, right? So you have a hole in the 2p state. The same, so both are looking identical, but the way it reaches this final state, it actually achieved through different routes. So here there is a decay from the neighboring atom happens first, and the ionization occurring in the here, right? So these decay mechanism, they are called ICD. So this one we call it as direct ICD, and this process we call it as exchange ICD. And then there is another process that can happen, which we call it as electron transfer mediated decay. So here what happens, again, here first you have ionization will happen here, that will create a vacancy. And then this vacancy is filled by an electron from the neighboring system. And this energy liberated, it will now ionize the same system, right? So here you can see that the two holes that are present in the same system. So if you look at these two cases here, the two holes are present in the two sides, two different sides. But here, these two holes are present in the single side. So this is actually demonstrated for the case of neon-argon dimer. So these are the different energy levels for neon and argon levels. So you can see that. So this is argon. So first you have ionization happening in the neon. So you have a vacancy, and this vacancy is filled by an argon electron from the argon atom, and the energy liberated will be used to ionize the argon atom itself. So you get argon 2+ in the system. So initially you started with a hole in neon. You started with a neon plus or neon ion, but you ended up with argon 2+. So this decay mechanism is known as the electron transfer mediated decay. So these are the energy levels of this system. So here again, you can see that the 3p, so the energy required to create these two holes in 3p, so that lies below this 2s hole level. So that means it can decay. So if you create a hole here, it can decay to this state. So whenever you have, so this is the main point here. So whenever you have a decay whenever you have ionization that happens in the inner shell, many interesting things can follow. So it can lead to radiative emission, that is popularly known as the fluorescence. But in addition to the fluorescent process, you can also have a non-radiative process, which is the OJ process, in which electrons will come out instead of photon. So these two processes actually they compete each other, and OJ decay that occur much faster compared to the radiative decay. So whenever these two processes can occur, the OJ decay will always dominate. Okay, so all these are mainly the theoretical predictions. So unless you verify it using some experiments, then physics as a subject, it is an experimental field. So if we don't have an experimental proof, then all the theories are not well appreciated, however beautiful it is. So how do you verify the existence of this ICD? So the basic idea is very simple. So as I said earlier, so because of this ICD, you create two holes in the neon atoms. That means you get two neon +1 ions, right? So you get this positive charge here. So because initially your neon is a neutral system, and then you are creating a hole here, right? So you have a neon plus, and the adjacent neon atom, it also has a neon plus. So you have something like two positive charges. They are close to each other. So that means they will repel each other. and it has a technical name which is known as the Coulomb explosion. I think it's essentially because of the Coulomb interaction. Because of this repulsion process, these two move away from each other. So the bond will be broken and these two will be move, and they will move in the opposite directions. So if you can come up with an experiment which can detect these ions, then we can say that we can verify this. We can confirm the existence of ICD. So this measurement, so we have to do it in a. So before that, before discussing that experimental work, so let us see what is the energy that will be liberated. So you can see that, you can easily see that during this process, so you have this 48.48 electron volts. So that is the energy required to create this 2s hole. And then to this 2s hole, this electron is getting decayed, right? And then with that energy, it will ionize electron from the neighboring system. So that means the final energy that is available will be 48.48 minus 2 times 21.66. So the balance energy in the process is going to be 5.16 electron volt. So this energy will be shared between these two neon ions and also the ICD electron. So this is basically the system. So you have two neon ions, neon cations, which will move in opposite directions. And then you also have the ICD electron. So people have done this experiment for this neon dimer, and they could clearly see the these two neon ions. You can see this graph here. So this is something, if you just look at, so these are actually the momentum of these two ions. So if you just imagine the graph of something like y equal to minus x, so this is the kind of structure you get, right? So the both electrons, they move with equal and opposite momentums. So in their experiment, they could discover this. So that is a very clear signatures of the existence of ICD. So you can also see here that, okay, so let me, so for this experiment, so they actually used photon energy around 58 electron volt. So that means 48 electron volt is the ionization threshold for the 2s. So once you ionize the 2s electron, so that electron will come with almost 10 electron volt photon energy, right? We can just use the Einstein equation. So you can see that these photoelectrons appearing here, so that will have energy of around 10 electron volt. And then once you have the 2s hole, then all this decay process happens. And then you create these two neon plus ions and the ICD electron. And these three species, these two neon ions and the ICD electron, they will share the remaining energy. And that remaining energy is around 5.16 electron volt. And that is what you see here. So this is like a straight line because you have two neon plus ions plus the ICD electron energy. So that will be a constant. So that is why you are getting a straight line here. So this is a very clear, very simple experiment with a clear signature of the ICD. So this experiment is done at Berlin synchrotron facility, and they use this cold trim setup. And so now, I think now you are clear about this inter-Coulombic decay. So it is essentially a non-radiative process. And so what happens in this process, you have an inertial ionization occurring first, and then you have a decay. And the energy liberated will be used to ionize the electron in the neighboring system. So you get two holes in two different atoms. So that is why we call it as interatomic Coulombic decay. So this cluster physics, so this is one of the interesting application of cluster. And then the cluster physics got a big boost with the discovery of this fullerene molecule. So this was discovered in 1985. So these are, as I said earlier, so these are formed due to the carbon atoms. So they form this football-like structure. So you have a lot of empty space inside. So this is the team that discovered this fullerene molecule. So this is so they discovered actually fullerene C60. That means 60 carbon atoms. They form this structure. So they got the Nobel Prize in the subsequent year, I think. And so I think before the discovery, there is one architect who designed something like this, which resembles the shape of this fullerene. And his name was Buckminster. So this also known as the, so just to honor his name, so we also call it as buckyballs or Buckminster fullerene. Okay, so then after the first discovery, then there are many different forms of or different avatars of fullerene was discovered. So this is C20, that means 20 carbon atoms form this cage-like structure. So this is C28, and this is C36, this is C50, and this is C60. So there are 60 carbon atoms, they form this football-like shape. And then more interestingly, you can also trap one fullerene inside the other, inside a bigger fullerene. So this is like a C60 fullerene that is trapped inside C190 fullerene. And here C60 fullerene that is trapped inside this C240. So there is a plenty of room inside. So in this molecule or in this, so you can view this carbon, this system as molecules and also as a cluster. So inside this hollow cage, there is a plenty of room inside. So I am again just making use of Feynman's famous statement, plenty of room at the bottom. But here inside this cluster, you have plenty of room inside. Room for what? Room for keeping atoms, or you can keep some clusters, or you can even keep molecules inside this system. So all these are, people have studied it theoretically, and then there are many experimental results which they could show clear signatures of these kind of species. So you can view this kind of system because you have an, so let's say you have an atom here, and this is surrounded by this cage. So you can say that this atom is under some environment. So this is an excellent opportunity to study how atom, molecule, and cluster will respond to environment, right? So normally when you solve Schrodinger equation, let's say for hydrogen atom, so we study for a simple isolated hydrogen atom. But in most of the cases, hydrogen atom is surrounded with something, right? Some environment will be there. And because of that environment, the properties of the hydrogen atom can get modified. So in our case, what we studied, so we have something like some atomic system, and which we keep inside this fullerene. And this kind of system, we call it as endohedral systems. So endohedral systems are nothing but the complex system formed, so where you trap atom, molecule, or cluster inside this fullerene molecules. So this kind of system has very fascinating applications. So they are promising candidate for atomic clock. And they are also proposed as one of the, for creating this qubit for this spin-based quantum computer. Because when you have, so this is for the nitrogen atom, which is kept inside the C60. And because of this C60, so C60 acts like a screen, or it's like a protector. So it will not, so it will keep the nitrogen atom safe from all the external interactions. So you can say that you can store this in qubit information in the form of spins in the nitrogen system, which is kept inside the C60. Because it is protected, then you will not have the effect of decoherence, which is one of the big problem in the quantum computing. So we can avoid or we can reduce some of this decoherence by trapping atom inside this fullerene system. And from a fundamental point of view, so they are model system to study how an atom. So here atom means that it can be atom, molecule, or clusters, how this atomic system responds to an environment. So this is when you say photoionization dynamics. So this I just discussed earlier. So you have an atom, then we have a photon, and it takes away the electrons. So you have this. So the neutral atom then becomes an ion, and then you have these photoelectrons. And these photoelectrons, so they carry the information about electronic structure. It can carry the information about the correlations, relativistic interactions, and the external confinement or the environment itself. So all these informations, you can get it by studying these photoelectrons. And to study that, we have certain parameters like photoionization cross-section, angular distribution parameter, and time delay. So by studying these parameters, so all these parameters are functions of energy. So you can vary the energy and you can calculate all of these parameters. And then studying this dynamics, how it changes with energy, you can get a lot of information about the target system. So this is an example for a cross-section for a hydrogen-like atom. So here you can see that the cross-section is proportional to the energy to the power minus 7/2. So essentially you will have a monotonic decrease. So at the threshold, so this is like 13.5 electron volt. So you have a maximum cross-section. So cross-section is essentially a measure of the probability of ionization. So you can have maximum ionization at the threshold, and as you increase the energy, that ion probability is getting reduced. But this is for a simple hydrogen-like atoms. And as you know that most of your system are many electron system. So there are many interesting phenomena associated with that. So instead of a monotonic decrease, so you will get sometime maxima, sometime you get minima and then maxima, and then you get a lot of fluctuations in the cross-section. So all of these spectra, so we can call it as a cross photoionization spectra. So these are like the fingerprint of the target systems. So by studying this cross-section or angular distribution or the time delay, so these are like the fingerprints of this system. So by understanding this, if you see some kind of a photoionization spectra, you can always decipher it is coming from which atom, right? We can always decode it. So these are like the finger signatures of individual atoms. So depending upon if you go from one atom to another, this will change. And if you have a Fullerene environment, that leads to the confinement resonances. So, but I'm not going to discuss this in this current talk. And so our primary focus is on this ICD. So this is an example of neon, which is trapped inside this Fullerene molecule. And here you can see that first you are ionizing neon atom from the 2s electron from the neon atom. So this is you are creating a 2s hole. And once you have this 2s hole, you can the 2p electron will fill that vacancy, and that energy liberated that will ionize the electron from the C60. Right? So ionization is the initial ionization is happening in the neon system. And because of the decay process in the neon atom, it will ionize electron from the C60. So this is again an ICD. Right? The final ionization is happening in the neighboring system or the environment, that is the Fullerene. So you get neon plus and C60 plus. So you have two ions in two different sites. But then, so like if you take C60, so each C carbon atom has 6 electrons. So you can see there are like 360 electrons, 60 carbon atom and 60 times 6, you have 360 electrons. So you can have many energy levels. And because of that, you can have a multitude of paths, multitude of decay paths that exist in such systems. So these are examples of these kind of decay mechanism. Okay, so I think so I hope you understood what is intercoulombic decay, and then I discussed what is the endohedral systems. Now the remaining thing that you need to understand is this plasmonic excitations. So this we can understood in a very simple way. So you know that if you consider metals, for example, one of the characteristic properties of metal is you have a lot of free electrons in the system, and these are kind of delocalized, right? So they are free to move within the system. So in totality, the system is neutral, but at the local level, you can see that you have free electrons are free to roam around within the system. And if you expose such kind of system to an electromagnetic radiation, then you can always create this kind of a charge separation in the system. So you can see that the positive part, so you can see that the electron cloud, they will move in a particular direction depending upon the direction of the electromagnetic field. And once the cycle changes, the direction will be opposite. Right? So you can have this kind of an oscillation between these two configurations. So you can have some kind of, you can make some kind of an oscillations in the system. So these plasmonic oscillations are nothing but the field-induced collective coherent oscillations of the free electrons in the metal. Right? So you can view it as something like a driven harmonic oscillator. Right? So you can view this kind of system as something attached with some kind of a spring. And then depending upon the electron cloud, and they will keep oscillating. So if you look at the example of a spring system, which is driven by some field with some external force, so you can see that there are at certain energies, it will have some resonance occurs. Right? At that energy, you will have the maximum absorption that can occur. And once this occurs, then that will be reflected in the cross sections as well. So whether it is in the absorption cross section or in the ionization cross section. So we call these are the plasmonic resonances. So these are actually plasmonic resonances that appears in C60, the fluorine molecule. Although carbon is not a metal, but to a good approximation, you can consider that the 2s and 2p electrons are kind of delocalized compared to the 1s electron. And you can treat this four delocalized electrons, and you can come up with some model, and you can theoretically predict the existence of such resonant frequency in the system. So this have been established earlier, so which is matched with the experimental results. So these are the plasmonic resonances that appears in C60. Right? So, and here, so this is actually the results from our work. So here, this is for the C240. So that means there are 240 carbon atoms. They form a football-like structure. And then you are exposing this system with the electromagnetic radiation. And because of this plasmonic absorption, you get this plasmonic resonances present in the system. So once it is excited, it will, so whenever a system is excited, it will always try to decay. And so this is what we studied. So you have this excitation happens, and because of after this excitation, it will follow up with a de-excitation, or it will follow some decay path. So you have this fluorine, the giant fluorine, that is C240, and the sodium-20 cluster is trapped inside. And because of this radiation, you have plasmonic excitation that happens in this C240 system. And so you can see that, so this is, you can view this as like an excited state, but this is like a collective excited state, and it will decay. And once it decays, energy will be liberated, right? And this energy can be used either to ionize the electrons that are present in the C240, then that is not an ICD process, because your ionization or the excitation that is happening in the C240, because the vacancy is created, this collective hole is created in the C240, and the ionization, the follow-up ionization is happening in the same system, the C240. So this is like an OJ process that we discussed earlier. But there is also a probability that once the decay occurs, it can transfer the energy to the system that is inside. And once that happens, you will get ionization from the sodium cluster. So we call this is an ICD plasma. So this is the kind of spectrum that I shown earlier. So this is for the combined system, that is sodium-20 inside C240, and this is the spectrum from the C240, which does not have the sodium-20 inside. So if you just look at these two spectra, you can see that this combined spectra has two additional lanes here, right? So these are coming because of the transfer of energy that occurs due to the decay of the +1 excitation, and that is used to ionize the sodium cluster. So this is what we theoretically predicted, that if you trap sodium cluster inside this giant fullerene, you can, and then you expose the system to electromagnetic radiation, you get photoelectrons from the sodium cluster inside. So if there were no C240 outside, then you will not get at these energies. So this will happen around 11 electron volt, this +1 excitation. So at this energy, you will not see any signals if it is a free sodium-20. But if you confine inside C240, you will get these additional signatures. So you can see that all the traces, they peak within this 11 to 12 photon energy range. And this is the energy range where the +1 excitation happens in the C240. And you can see that this spectrum from the OJ, so the spectrum from the C240 contribution, that almost remains the same. So these two panels, they differ only in these two additional lanes, and this coming because of the ionization from the sodium cluster inside. And this kind of thing, you can experimentally verify it using this velocity map imaging techniques, because you create these electrons here, and which are accelerated by some electric field, and depending upon the energy levels, they will come and fall in this detector. And from that spatial information in the detector, you can work back and get the momentum associated with that electron, and then you can see from where these electrons have come out. So you can see that these are the photoelectron energies. So in the vertical direction, you can see the photoelectron energies. So if you perform an experiment, so you will able to see this kind of additional signals in the detector. So what we did is actually a theoretical prediction. But to do this in an experiment, it has many challenges. So some of the people are working on this. So maybe in future, they may be able to perform this kind of experiment to verify our prediction. Yeah, so maybe I think maybe I will skip this slide. I think all the main information that I want to convey is already done. Okay, so I hope this is my final slide where we discuss the summary and conclusion. It is essentially the same slide which I used earlier. So I hope now this will be clear to you. So we discussed this intercoulombic decay, and here we call it as intercluster coulombic decay because you have a sodium cluster inside, and this giant fullerene is also considered as a cluster. So whenever you have two clusters, we call it as intercluster coulombic decay. So for the neon case, we have two neon atoms. That's why we call it as interatomic coulombic decay. So you have intercluster coulombic decay, which is essentially a non-radiative transition. And then, so you have a photon which interacts this giant fullerene and it excites the plasmons in this fullerene. And when it decays, then you will have this OJ process that will ionize the electron from the C240 system itself. And then some part of it will be used to ionize the electrons from the sodium atom, sodium cluster inside. Okay, so basically what you see is that by exposing one part of the system, you can initiate some process in a neighboring system, in a remote system. So you can control, so you can make some kind of a remote control. So you do something on some part of the system, and because of what is happening there, that will have some impact on the neighboring system. So you can have a remote, you can kind of have a remote control effect. So that is one of the importance of this. So this is, so what we have predicted is very fundamental. So we have shown this for this particular system, sodium 20 inside C240, but we believe that this can be seen in other kind of systems as well. Okay, so this is my group here. So most of this work is done by Rashid. So you can see with this star t-shirt. And most of our work is funded by this DST CRG project. And I'm fortunate to collaborate with many people across the globe. So for this particular work, I collaborated with this Dr. Himadri Chakrabarti and Dr. Majid and his group in Germany. Yeah. Okay, so that's all. So maybe it's open for questions.
Okay. Thank you, Hari, for the wonderful talk. So now we can take questions. So let me start first. So I had a question about this. So you had that graph, no, about this plasmonic excitations where you showed sodium fullerene, sodium inside fullerene. That graph.
This graph?
No, earlier. That you had a graph.
Okay.
So just after discussing plasmons and all.
Yeah. Yes. Let me... Okay. This graph probably.
Yeah. So actually over here, I mean, I don't see much of a difference between C240 and sodium inside C240.
Yeah. So you're referring to this graph, right?
Yeah, the red and blue lines. So, I mean, are they?
Yeah. So this is actually the total cross sections. So total cross sections include both the sodium levels and the carbon levels from the carbon atoms.
Okay.
So it is not just the sodium 20. So what you see here, this is the total cross section. So that includes all the subshells from sodium and then all the subshells in the fullerene.
Okay.
So the total cross section, you may not see much difference because the entire process is dominated by this giant plasmons in the C240. So the blue curve here, so that is the C240. And the red curve that you see here, that is the sodium 20 at C240. But both represents the total cross sections. So the actual contribution to the from the sodium, so that is relatively less compared to the contribution from the C240. So here you cannot see any distinction, but when you do this, where you are actually making a distinction based on their velocities. So here you can actually make a distinction between the sodium levels and the carbon, this fullerene levels, because the fullerene, so these are corresponding to the photoelectron kinetic energies. And these kinetic energies of electrons from the sodium cluster and the sodium and the fullerene electrons, these kinetic energies will be different because the binding energies are different for the sodium subshells and the fullerene subshells. So you have a kinetic energy on the kinetic energy level. So there will be a distinction. And using this experimentally, you can do this by using this velocity map imaging techniques.
Okay.
So you
Okay.
have
Yeah.
some kind of an electric field. So these electrons will come out with different energies. And depending upon these different energies, they get accelerated in this electric field. And since their initial conditions are different, so they get a different image in this detector. And from that, you can actually work back and get the information about the kinetic energies. We can work back and get the information about momentum and then the kinetic energy. And then you can get, we can say that whether it has come from the fluorine electrons or from the sodium.
Okay. Okay. Yeah, I understand. Yeah. Thanks. And one more question. So, you talked about people working to experimentally verify this prediction. So, is that your group or groups elsewhere?
Yeah, so these are groups elsewhere, not here. So these are some German groups. So we contacted some of them. So because the kind of system that we considered, this is sodium. So this is like a sodium 20 means a metallic cluster. So which is inside this fluorine. So creating this kind of system is not very easy from an experimental point of view. But since we have made this prediction, so some of them have shown interest. So now they are working on it to see whether they can get it. But for the neon case, that is already verified. So that is done at Germany. This is at the Berlin synchrotron facility in Germany.
Okay. Okay. So thanks, Hari, for answering those questions. So let us now, throw the floor open to questions from the students. I have, so students can unmute and ask questions. അതായത് ആർക്കെങ്കിലും എന്തെങ്കിലും ക്വസ്റ്റ്യൻസ് ചോദിക്കണമെങ്കിൽ അൺമ്യൂട്ട് ചെയ്ത് ക്വസ്റ്റ്യൻസ് ചോദിച്ചോളൂ. യു ക്യാൻ ആസ്ക് മലയാളത്തിലോ അല്ലെങ്കിൽ ഇൻ ഇംഗ്ലീഷ് ഓൾസോ യു ക്യാൻ ആസ്ക് ക്വസ്റ്റ്യൻസ്. ഓക്കെ, യാ പ്ലീസ്. Any questions? You can also put up your hand if you wish.
So actually I did not discuss the modeling aspect of these systems. So I think so many of you may be knowing that, I mean, you solve hydrogen atom by just doing analytically, right? You solve the Schrodinger equation, which you can do it analytically. But when you come to this kind of system, so you have many electron systems, so which you cannot get a exact answer. So you have to use some kind of approximations. So you can view like each electron is moving in some kind of an average field. And then you can set up the equations and then you have to solve it in a self-consistent way using some, so that you have to solve it numerically.
So did you use some codes written by your group, or was it done in some software, the simulations?
No, we did not use any software as such. For this work, we had some existing code in the group. So we have this collaborator, Himadri Chakrabarti. So he has developed some part of the code. Then we have modified it to serve our purpose. And then we did all this calculation based on this modified code. And to get some support, we collaborated with some quantum chemistry group in Germany. So they did some molecular level calculations. So they use some software, some quantum chemistry based software. So we got a good agreement between our results and their sophisticated molecular level calculations at the ground state level. But for the ionization, we depended on the codes that we had in the group.
Okay, and is there any follow-up work that you're doing, building upon this work for some other system or?
So now we are also interested in what is this time delay associated in this ionization process. So this is because of the recent developments in this attosecond physics. So this time delay associated with many of this photo emission that will be in the attosecond range. So we want to study some of these aspects. And then we are also interested to get some more detailed understanding of this ICD in this particular system. And of course, yes, we can also try for some other systems where we can predict similar features.
Okay.
So now we have seen actually with the photon collision. Photon is interacting with the system. But the similar thing you can also do with an electron impact ionization. So that is another direction we can pursue.
Okay, and can you also comment on what can be the applications in technology of this process? You had earlier mentioned about how ICD, and so it has applications in various quantum technologies and all. So this particular process, do you have any comments on applications to technology?
So technology wise, so one of this application of ICD that is mainly in this cancer therapy. So when you expose a cancerous cell with a radiation, so essentially that is a light matter interaction. And once, so that induce some excitation in the body. And once that excitation happens, associated with that, you will have many decay process that can happen. So in the case of that neon example, we have seen that when you ionize the electron, so that is the primary electrons. So that will go up an energy about 10 electron volt. But the ICD electron, so that comes because of the decay mechanism. So that is, it will have an energy below 5 electron volt. So compared to the primary electron, the secondary electrons are slower. And whenever this, in cancer therapy, what happens, whenever you have this excitation and the decay happens, so many of these slow electron decay mechanisms, because of this many decay mechanism that could happen in the body. So there can be many slow electrons, and that actually destroy the many of our non-cancerous cells. So by studying ICD, you can get some information about this kind of slow electrons that happens because of the decay mechanism. And the similar process also occurs in interstellar medium. So where again, because of the interaction of light with molecules and clusters. So there again, you get many of these slow electrons, and these slow electron initiate many other processes in the system. So you can get a lot of information by studying this ICD. So if you specifically ask for this particular system that we considered, so currently we don't, currently it is not experimentally feasible, so we don't envisage any immediate applications. So it is more of a fundamental, the prediction is more of fundamental in nature. And we see the existence of this phenomena in this kind of system.
Okay. In the case of cancer, what you're saying is that what we would like to do is to understand these slow electrons and somehow remove them so that they don't damage the body.
So the slow electrons are responsible for damaging the body. So to understand how this damage occurs, so we need to understand what are the different decay mechanisms that can happen, that will happen in a system. So ICD is predicted in water molecule as well. So since our body contains mostly water molecule, so it is expected that there will be many ICD process that happens in our body when it interacts with this kind of radiation. So we hope that by studying ICD, we get information about this kind of slow electrons. So once you understand that decay mechanism, maybe we can control the damage that follow up because of this.
Okay, all right. And
it's like a prospective application. People are working on it, and then.
Okay, yeah, I understand. So Yeah. So any questions from the audience? Please unmute yourself. Unmute ചെയ്ത് questions എന്തെങ്കിലും ഉണ്ടെങ്കിൽ ചോദിക്കാം.
Yes.
Okay, so if there are no questions, then let us thank Hari again, okay, for this very nice talk. I mean, so I really enjoyed the talk because I understood. I mean, even though it is not my
Thank you.
field,
Thank you.
it was a very clear talk. Okay.
Okay.
So thank you for the talk. Okay.
Okay. So
Yeah,
if any of you are
that's-
interested to do some small project, or you can always write to me. And so as I said, our PhD application is on. So I encourage all of you to apply for it and give this information to your friends as well.
okay. Yeah. So thank you, Hari, once again. And now we shall end the meeting. Okay. Thanks everyone for participating. Yeah,
Okay.
we are ending the meeting. Yeah,
Thank
thanks.
you. Thank you, Krishna, for this opportunity.